Our result from the last video was a simplification that we're going to use a lot to save ourselves some effort. And that is, if we're trying to calculate the torque on some object about a fixed axis due to gravity acting on that object, at least superficially it looks like the problem is very complicated because gravity is pulling on lots of different bits of mass, and so there are lots of forces with lots of different moment arms. Here I've labeled the moment arms for each bit of mass m1, m2, m3 as x1, x2, x3. And we have to add all those forces times moment arms up together to get the total torque, gravitational torque about this. But we found out that if we define something called the x-coordinate of the center of mass, then we could calculate the net torque due to gravity, which is really due to all these little forces, by pretending that there's only one gravitational force and it acts at a location that's called the center of mass of the object. And all we have to do is pretend the full force is acting at it. So the center of mass here is denoted by, it's a location, and it's denoted by this little black and white circle here. If we pretend the full force, the total mass of the object times little g, acts at this location, then we only have to use the corresponding moment arm, which we would call the x-coordinate of the center of mass, if x is the direction perpendicular to the gravitational direction when we calculate. So the statement is down here in blue. If you need to calculate the gravitational torque on an extended object, you can pretend the entire weight force is exerted only at the center of mass and use the corresponding moment arm. Here's a different way to think about it. Things aren't always lined up so neatly. In other words, the center of mass isn't always horizontally displaced from the axis, but here's how it generalizes. Here's an object. It's some irregularly shaped object. There's a fixed axis which comes out of the computer screen right here, and the object can rotate around there, and it's in a vertical plane, so gravity is going to try to move it down and get it to rotate around the axis in this direction. We want to calculate the torque due to gravity. To do that, what we do is divide up our object again into lots of little pieces, and using those little pieces, we can find the location of something called the center of mass. The center of mass is a point in space, which is something that's going to simplify our torque calculations. At least that's what we're going to use it for right now. And to calculate the location of the center of mass, we of course need some coordinates. So here I've drawn in some x and y coordinates. It doesn't really matter what coordinate system you use, but usually if we're talking about gravity, it's convenient to take one of them vertical and the other one horizontal. And once we've done that, we can define what the x and y coordinates of the center of mass are. And to do that, we just multiply the mass of each of these little bits times its corresponding x-coordinate or y-coordinate in the other formula, add them all up in the numerator, and then divide by the total mass, in other words, the sum of all the masses of these little bits in the denominator. What you're left over with has units of distance or position, right? So it'll have SI units of meters. And once we found that center of mass location, we know its coordinates, we can pretend, the result is, that the entire force on this whole object is being exerted only at this one point. So it's as if we've tied a string attached to this one point and it's pulling down right there. That's the total effect of gravity on all of these. Okay, that's not completely obvious on the face of it. So that if we want to calculate the torque, well, one way to calculate the torque is to use what's called the moment arm. We draw the line that contains the force that's being applied. So I draw that line and I figure out what that shortest perpendicular distance is. We call that r perpendicular, or the moment arm. And the magnitude of the torque is equal to r perpendicular times the magnitude of F. That's one way to think of it. How big the force is times the moment arm. And in this case, the force is just the full gravitational weight force, mg times r perpendicular. Now in doing this, this is just the magnitude of the torque. If we want to assign a sign to, okay, before I say that, so again, this is the same text that was on the previous slide. If you need to calculate the gravitational torque on an extended object, which seems on the face of it complicated, you can simplify your life by pretending the entire weight force is only being exerted at a single point, which is the location of the center of mass. And here's how you find the x and y coordinates of the center of mass. And once you use that approximation, or it's not an approximation, it's really just a simplifying principle that the force is as if it's being applied at this one point, you find the corresponding moment arm and use that to calculate the torque. What I was going to say is that only gives us the magnitude of the torque. In order to give a sign for the torque, of course, we have to choose a positive rotation direction, and that means in this particular example, the picture I've done here, this weight torque due to the weight force is actually going to try to twist it in the negative direction. So if I wanted to really get the sign of the torque correct, given this convention for the positive direction, this would be a negative torque around that axis where the positive is defined there. Now we're going to get a relationship between angular acceleration and the angular analogy to force, right? Torque is like force, alpha is like acceleration. It's our angular acceleration. So that's like the relationship between F and A, F equals ma. And of course that's where we're going to start with, and we're going to try to change it into torque equals I alpha. So what we'll do first, same object, there's a fixed axis on it. Doesn't have to have any special shape. We're going to divide that object into a bunch of little tiny bits of mass. So I put a grid over the top of it. And we're going to focus at first just on one tiny little bit of mass. And then we're going to add up all the effects in the end. But let's just focus on one to simplify. That particular little bit of mass there has some net force acting on it. And that net force could be due to a lot of things. Not least because that little bit of mass there has some neighboring bits of masses that are pushing on it. So they're exerting some force on it. Even if I'm not pulling on this point, if I pull at some other location on the object, that will be transmitted to M1 through its neighboring bits of mass. So part of this F1 net might be the neighboring bits of mass pushing on it with forces, but I also might have a bit of string attached to that and I'm pulling on that in some direction. In any case, we're adding up all the forces on M1 and I'm just imagining it points in the direction shown. Now M1, as this object moves, M1 is going to move in a circular arc, right? As it starts, if whether it rotates down or rotates up, M1 is going to start moving along a circle, and it's got a certain radius. I've called it R1 to go along with the one on the M1. And once we've defined that circle, we can draw a direction that is tangent to the circle and pull out what the tangential component of the net force on M1 is. So I'm calling that F1 net tangential component. Okay? Now, what we're going to do is write down F net equals ma for tangential components just for M1. So here's F net equals ma for mass M1, the tangential components. And since I want to change this into a torque, I'm going to multiply by the moment arm, right? So if one way to think of this is if I want to calculate the torque, the net torque just on M1 due to all the forces acting on it, I could multiply the radius times the perpendicular component of the force. So I'm going to multiply by that R1 on the left, and of course I can do that if I multiply by R1 on the right hand side of the equation too. So there I'm just multiplying by the same thing on both sides. And this, as I just said, represents the torque that is being applied to this object by virtue of the forces that are acting on just M1. So we might call that the torque just due to the forces that are acting on M1. That's not the torque on the object, it's just one tiny bit of it. Okay? And on the right hand side, what I've done is used our relationship between linear and angular quantities we got before. We found out that the tangential component of the acceleration is equal to r times alpha when something is rotating about a fixed axis. So M1 is moving on a circle of radius r1, so that gives us another r1 times alpha. And the alpha I don't need to put a 1 on because there's only one alpha for this entire object, right? If the object is rotating, the whole object has an angular acceleration. That's why I didn't put a 1 on there. So that gives us an r1 squared on the right-hand side. Similarly, now to generalize to the entire object, I could find another bit of mass and call it M2. M2 is also moving on a circle, and we could find its net force on M2 and take its its tangential component and so on. We could do that for all the little bits of mass in this whole thing. We get a relationship like this for M1 and M2 and M3 that would have 1s and 2s and 3s in it, all the way up to 1,000 maybe. And if we added all those equations together, the left-hand sides would have all the torques on this object about this axis due to the net force on M1 and M2 and M3. So that would be the net torque on the entire object about the axis. And on the right-hand side, adding all those 1,000 equations together, we get M1 times R1 squared times alpha plus M2 times R2 squared times alpha. And it's the same alpha for all of them. So all I've done is factor out that common factor of alpha on the right-hand side. And as we've done before, we're going to give a definition for this thing that's in parentheses here. We're going to call this thing in parentheses M1 times R1 squared. So that means when you're rotating about a fixed axis, the little bit of mass times its distance from the axis of rotation squared. Add that up for all the bits of mass, and we're going to call that the symbol I, and the words are moment of inertia of the object about the axis, or the rotational inertia of the object about the axis. Okay? It's a property of the entire object with respect to the axis, and as it suggests, it is analogous to good old inertia. Remember, inertia is the same thing as mass, and it measures the resistance of an object to linearly accelerating, right? What is the definition of a mass of an object in outer space, right, where there's no weight to the mass? Well, it tells me how much it resists linearly accelerating. Here, the rotational inertia tells me how much an object resists accelerating in an angular sense about a fixed axis. So, you might have a phonograph record made out of plastic, and it's pretty easy to accelerate about the center axis. And if I compare that to a big, massive barbell plate, and if I have to really heave that thing to get it rotating about the barbell thing that it's attached to, it would have a huge rotational inertia. It doesn't want to start angularly accelerating. So that's the idea of that name, rotational inertia, anyways. So in terms of that, on the left-hand side, we have the net torque on the entire object. That's just being, the torques on all little bits of mass about the axis is the total torque, or the net torque on the object about the axis. And that's equal to the moment of inertia times the angular acceleration. Torque net equals I alpha. So that's our new F equals ma for rotational motion. It's been re-expressed in terms of the rotational analogy to force and the rotational analogy to acceleration. This is angular acceleration. And the rotational analogy to mass is the rotational inertia or moment of inertia of the object. In this case, there are signs that are important here. We don't want to mix up the minus signs between the left-hand and the right-hand side. So we're going to call, again, a torque positive when it tends to rotate the object in the positive direction. And alpha, of course, is positive if, well, we've talked about when alpha is positive. If the object is speeding up in the positive direction, that's a positive alpha. Or if it's slowing down in the negative rotation direction, that's also a positive alpha. And both of these things on the right-hand side are properties of the entire object with respect to the rotation axis. In other words, how fast it's angularly accelerating is not a property of a point on the object, but rather of the object as a whole. And how much rotational inertia it has is a property of the object with respect to the axis. Okay, let's do a few voting questions. Here we've got a meter stick with a rotation axis at the center, the 50 centimeter mark, and the same meter stick where we've fixed it so it would rotate around one of the ends of the meter stick. How do the moments of inertia of these two axes compare? In other words, the moment of inertia of this meter stick about this axis, how does it compare to the moment of inertia of this meter stick about this axis? And for your reference, I've put the formula for the moment of inertia, which we got on the last page. Think about that for a second. The answer is B, that the moment of inertia about the end axis is larger, and it comes from this formula here. The r's are different, and what I can do is divide the object kind of up into two pieces, the gray part and the green part here. And we can see that, if I'm dividing this object into a bunch of little bits of mass, there's a little bit of mass right here, and its distance from the rotation axis would be this little distance here. Well, I've got the same little bit of mass in this one. It's got the same distance from the rotation axis there. So if I'm dividing these up, all little bits of mass and their distance from the rotation axis are going to be the same for this gray part here and this gray part here when we're adding them up. So that's half of the things we have to add together. But the green parts differ, right? If I take this part halfway out, the green part, it would have a distance of 1/4 meter to the axis of rotation. That same part in the second piece is going to appear out here, and it's going to have a distance, the center of the green part, to the rotation axis of 3/4 of a meter. So all the r's have gotten bigger in this case, and that means the m's are the same. They've got the same little bits of mass in this green part as this green part, but the r's, the distance of those m's to the rotation axis, is bigger. So those r squareds are all going to get bigger, and so this second case has the larger moment of inertia, I, in that case. All right, here is a demonstration of something that I usually pass around and have people try out in class. So we have these exact kind of wands that this physics professor is going to explain to us, but watch the video and notice how he's using them.
This is a demonstration of moment of inertia. I have here two rods, one red, one blue, and I want to first demonstrate that these rods have the same mass, about 1.15 kilograms for the red one, and 1.15 kilograms for the blue one. But the mass in these rods is distributed differently. In the blue one, the mass is distributed near the ends, and in fact you can see here that there's mass covering these holes. And if I use all of my amazing strength to try and rotate this as fast as I can, this is as fast as it goes for me. It's hard to get started rotating because the mass is farther away from the axis of rotation, which is along the line of my forearm. As opposed to, for this red rod, the mass is not out here at the ends, but instead it's here concentrated very close to my hand and concentrated close to the axis of rotation. Very easy to turn this, very easy to start the motion, and so this helps, hopefully helps you understand that moment of inertia acts like mass but for rotations. It's harder to get this one moving, harder to get the blue one moving than the red one because the blue one has a much larger moment of inertia. It's moment of inertia.
All right, so what he's demonstrating there is that the moment of inertia is larger because the r is larger. We had the same mass in those two rods, but in one case the mass was almost all out at the outside of the rod, and that means the r squared in the first case is all the way out at the outside. And in the second case it was near the center, so same mass but near the center, and that means when we're adding up all those m3 times r3 squared, all the r's are smaller for that huge amount of mass that was in, either out at the outside or the inside. That makes the rotational inertia bigger in one case where it's at the outside, and what that means is it's more difficult to angularly accelerate the object about that central axis. So that's another way to see it. Even though the mass is the same, it depends on how the mass is distributed, how far away the mass is from the axis. This slide here is something that you saw in the book, and it demonstrates what the moment of inertia is. Someone's done all that adding up in the definition of the moment of inertia. They have to do some calculus, do an integral to add all those things up for various common shaped geometrical objects about an axis that's displayed on here. As we found out from that voting question, you have to be careful to specify what the axis is because the moment of inertia can change when you change the axis. In this case, here is a solid cylinder or disk. In other words, we've got the axis going through the axis of symmetry of the cylinder. It could either be really long along that axis direction, or it could be really thin like a barbell or something. Notice that the formula, the moment of inertia, is the total mass of this thing times the radius of the disk, that circular part, its radius, squared with a 1/2 out in front of it. And it doesn't depend on the thickness of the disk or the thickness of the cylinder along the axis direction. So it could be really thin. We could think of it as a thin disk or a thick cylinder. It doesn't matter. If you do all that adding up for a thin hoop around the symmetry axis, so it's going in the direction perpendicular to the plane that contains that almost circular hoop, then it's just m times r squared. In other words, it doesn't have the 1/2 out in front of it. If you take a solid sphere of uniform density about a central axis, it's 2/5 mr squared. So that r always refers to, if you have a circular cross section, what's the radius of that circular part of it. Rod about the center, that's like our meter stick pivoted to rotate about the center. It's 1/12 ml squared, where m is the mass of the stick and L is the total length of the stick. Whereas if it's pivoted about one end, it's got a moment of inertia which is larger, in fact larger by a factor of 4. This is larger by a factor of 4 than this particular one here. So the moment of inertia is 4 times as large, it's 4 times as difficult to angularly accelerate. We won't tend to use these ones over here in that part, but those are the most important ones. So I just wanted to point out again that in this case, the moment of inertia of a rod about an end is 4 times as big as the rotational inertia of a rod about its center. That's relevant for this voting question. Here it says, consider a meter stick with a rotation axis about its center, and the same meter stick with a rotation axis about one end. If a force F is applied in the direction out of the screen, in other words, somebody puts their finger on the meter stick and pushes in the direction out of the screen, the computer screen, with a force F right there, and we observe a certain angular acceleration of this about the axis at that, just for a very short amount of time of applying that F. Where in this second case, where we pivot the object for rotation about the end axis, where should we apply the same F out of the screen in order to make it angularly accelerate with the same angular acceleration? At the axis, should we push there out of the screen, or here out of the screen, here out of the screen, here out of the screen, or at the very end out of the screen? In this case, the correct answer is E, and that's from torque net equals I alpha. In this case, the I, as we observed on our last, in that slide that shows all the different moments of inertia of common geometrical objects, the moment of inertia increases by a factor of 4 here. So if I want to get the same alpha by virtue of torque net equals I alpha, if I has gotten 4 times bigger, the net torque better have gotten 4 times bigger if I want the same alpha to result. And if I want to make the net torque get 4 times bigger, here the force had a moment arm of 1/4 meter. I better make that moment arm 4 times as big, and 4 times 1/4 meter is a full meter. So we'd have to push out of the page or out of the screen with the same force at this location right at the end if we want this one to angularly accelerate about this axis at the same rate that this one is angularly accelerating about that central axis. Okay, let's start a worksheet problem now, and we're actually going to have to do part A together because it's a little bit unfamiliar. Here we've got, in this case, a pulley, but it's not like the pulleys we've used in the past. This is a massless pulley, and it's actually not even frictionless. There's a friction, so it's pivoted to rotate about its center, but you can think of it like a massive barbell. It really doesn't want to get started rotating, so it's not like our massless pulleys we considered before. And there's also friction acting at this central rotation axis too, and we're told about that in the problem. And we've taken a string and wound it around the pulley and then let it dangle off the end and is attached to a mass here. So this cylinder up here, we're going to imagine, is a uniform circular cylinder of mass 2 kilograms, and it has a radius of 20 centimeters, and it can rotate about the axis through the center. And as it rotates, there's a friction force at the axle, which exerts a torque in the direction opposite the rotation. And I guess I don't tell us what that torque is, but maybe in this version over here I do. Yes, so that didn't have the right information in it, but in this version here I've said the frictional torque has a magnitude of torque of 1.1 Newton meters in the direction opposite the rotation. So that frictional torque always resists the rotation direction. We wind a light string around it, so we're going to assume the string is effectively massless, and a 1/2 kilogram mass is hung from the edge of it. And the question is, what is the angular acceleration of the pulley? And in this case, the way we're going to answer that is, remember when we did the Atwood's machine where we had different blocks hanging on opposite sides of one of those massless, frictionless pulleys? We did a separate F net equals ma and free body diagram for this one and the one hanging on the other side. We're going to kind of do the same thing here, except we've only got one block, so we'll do F net equals ma, a free body diagram for this. And then we're going to do torque net equals I alpha for the rotating object. And that's going to give us two equations in two unknowns. The first thing that's important, you remember when we had the two masses hanging on either side, it was important to choose a consistent direction for what we call the positive direction in our free body diagram. It's going to be true in this case too. What I want to do in order to not get confused by minus signs is whenever this mass is moving in the positive direction, I want this rotating object to be moving in the positive rotational direction. So in this case, I've taken counterclockwise to be positive and downward to be the positive direction for this. And so that's consistent. When one is rotating in the positive direction, this one will be moving in the positive direction. And what that means is the relationship between the acceleration of this one and the angular acceleration of this one is just ay equals r alpha. The y acceleration, if I call plus y is down here for this one, its y acceleration is equal to the radius of this one times the angular acceleration of this one. Why is that? Because we already know that the linear acceleration, tangential acceleration of a point on the edge of this disk, that tangential acceleration of that point is equal to r times alpha. But the point on the edge of the disk, its tangential acceleration is going to be the same thing as the linear acceleration of this block, and we'll just call that ay. So this one's y acceleration will be r, the radius of the disk, times the angular acceleration of the disk. We're going to use that below. That's a little bit complicated, but we're going to have to use that below and remember how to use it. Here's my free body diagram for the block that's moving vertically. Again, I've taken plus y down. It's got two forces on it, tension T going up, and it looks like in my picture here, I've done something incorrect. This should actually be a 1/2 kilogram. It looks like I changed my mind up there. So this should say 1/2 kilogram on it. It's got tension going up and the weight going down. This should actually say 0.5 times 9.8. So that's a little mistake. I think it looks correct over here in the work, but the picture is wrong. So that 2 should be at 1/2. If I do F net y equals may for that free body diagram, the weight comes in with a plus sign, the T comes in with a minus sign, the mass is a 1/2 kilogram times the unknown ay. And notice that I would like to solve for ay because it's related to alpha, which we're asked about, but I don't know T yet. So the first thing I'm going to do is, because we're concerned with alpha, I'm going to translate that ay using this relationship into alpha. So replace ay with the radius of the disk times alpha. And then I'm going to take that whole equation there, not using the middle part, and solve it for t. We'll see why in just a second, because I'm about to get a second equation and substitute. But so from just this free body diagram for the thing that's moving linearly, I've gotten this relationship between t and alpha. Let's hold on to that for a second. And then also do torque net equals I alpha for this rotating cylinder. Now, what about the net torque on this? Well, there are two things that are really pulling on it. Of course, the string is pulling down on it, and that's going to cause it to rotate in the positive direction because the tension is tending to pull it in that direction. Gravity's also pulling on all parts of this, but, you know, gravity's not tending to cause it to rotate one way or the other. That's one way to see that the gravitational torque on it is zero. Or we know from just the symmetry of the object that its center of mass is going to be at the center of the object. That's always true for any symmetric object. The location of the center of mass of a symmetric object is always at the center of symmetry of the object. So here's the center of mass. If we pretend that the full gravitational weight force of the entire disk is being applied right there, the moment arm relative to that axis would be zero, and therefore gravity is exerting no torque on it. In either way you understand it, the only torque that is going to contribute to the net torque on it is the torque due to the string. It's going to cause it to want to rotate in this direction about there. So the torque due to the string, it's as if the string is attached right at this edge. That's where it becomes attached to the pulley, and so it's pulling downward with a tension T, and the moment arm for that force that's being applied right there is the radius of the disk. So I've multiplied it by 0.2 meters, and it's a positive torque, so I put it in with a plus sign. T times the moment arm, and it comes in with a plus sign. That's the net torque, because there's only one torque contributing to it, and that's equal to I times alpha. That's our relationship we just got. And in this case, the I is the I for a uniform disk pivoted about its center. And if I go back to my slide that shows those common objects here, here is the uniform disk pivoted around its center. We're just going to imagine that this direction into the page is really thin. The answer doesn't depend on it, so the formula is still 1/2 mr squared if the object is really thin. So I'm using that back here in this solution. Notice the moment of inertia is 1/2 times the mass of the disk times its radius squared times alpha. So there's another relationship between T and alpha, and what I can do is solve those two relationships between T and alpha by using this entire expression for T and substituting it down here. Why am I doing that? Because I want alpha. I don't really care about T. Nobody asked me about it. And therefore, I'm going to solve for alpha by substituting for T in the second one. When I do that, so here's the full expression from T from this first one up here. I've placed it in parentheses next to the 0.2 that was there. And then I've got a relationship that only involves alpha. I can put all the alpha stuff on the right-hand side, all the non-alpha stuff on the left-hand side, combine like terms, and then divide out this number that's multiplying alpha to figure out what alpha is. And apparently, alpha is 16.33 radians per second squared. So that's the answer to part A. And now I want you to use that answer to part A, which I've just summarized there, to complete part B. And that says if the mass is released from rest, so we're just holding this thing motionless. I have my palm underneath here, so everything's just sitting at rest, and all of a sudden I release it, so this thing starts falling and this thing starts rotating. How long does it take for the mass to fall 1.5 meters? That's the second part to this question. And then question 2 you should also work on now too. Here is a uniform rod of mass 2 kilograms and 1 meter in length, and it's released from rest at the horizontal position. So it's pivoted to rotate in a vertical plane, so gravity's going to want to make it fall. I'm holding it at rest here. Suddenly I let go of it and it starts falling. When it's as it passes the point 30 degrees below horizontal, find the angular acceleration of the rod about this axis at that moment in time. We'll be back with the solution to that, but try those yourselves.